All right, guys, good morning. I am going to be going over some homework questions for chapter 1.3, the numbers you see in front of you right here. So I think after I'm done with this, I'm going to put the times for each problem on the bottom. So if you were like, I don't want to wait through 43, 51, and 61 just to get to 75, just look at the bottom and it'll tell you where 75 starts. So let's get started with number 43. Okay, so here is number 43. We are determining if this function is even, odd, or neither algebraically, which means we're not going to look at a graph. We're going to use the relationships that we know. So a quick reminder that for something to be even, that means that when I plug in a negative x, it's going to be equal to the original function. Because if you think about it on a graph, the negative x values are the exact same as the positive x values. That's why it's symmetrical over the y-axis. Whereas if something is odd, what that means is that the negative x values are equal to the opposite y values, which means, again, if you think of on the graph, that's why it's symmetrical about the origin, because if you're going back and up, then to be symmetrical about the origin, you would want to go forward and down on your graph. So yeah, that's what we're looking for. So what I'm going to do, I'm going to little zoomy out here. I am going to plug in negative x to this puppy right here, and just solve for, or not solve, evaluate what our function is at h of negative x. So I'm going to do that back over here. So h of negative x is going to be negative, and then I'm going to put my input in parentheses, just so I can make sure and keep it separate. And then that's going to be negative x squared minus 9. So be careful with your negatives here. This is a little tricky. So when I cube a negative x times a negative x times a negative x, that is going to get me back to negative x. So what that means is I have got negative times negative x cubed over 3. And then what happens here, I've got negative x squared, so negative x times negative x, that's going to get me to a positive x. So that's going to be 3x squared minus 9. So let's go ahead and address this double negative up at the top. I have a negative times a negative x cubed, excuse me, which turns that into just a positive x cubed over 3x squared minus 9. I can't simplify that anymore, so now the question is this h of negative x, is that equal to the original function? It is not, because there's a negative sign back in the original function that is not here, which means, I forgot about double lightsabers. Sorry, I forgot about double lightsabers, y'all. Let me scoot that down a little bit more. I'm going to write h of negative x does not equal h of x, so this is not even. Now what I'm going to do, let's try and see if it's odd. So to find if it's odd, I'm going to put a negative sign out in front of h of x. So that's a negative, basically times all of this, negative x cubed, 3x squared minus 9. So, y'all, I'm going to fix this parenthesis real quick. Y'all, please remember that when you are multiplying fractions, multiplying negatives, this guy right here is basically saying, like, this is negative 1 times all of that. And since this is a fraction, let's treat this as like a negative 1 over 1. So I'm just going to multiply straight across. So I'm going to do negative 1 times negative x cubed, and then a positive 1 times all this on the bottom. I don't want to put a negative on top and on bottom, because I can't do that, because a negative divided by negative would make it positive. So that would undo this negative 1. So there's only one negative to be had. So make sure you don't go crazy with your negatives. So on top, negative 1 times negative x cubed is going to get me back just a positive x cubed. And then on bottom, 1 times 3x squared minus 9 is just going to be 3x squared minus 9. Now, check this out. Remember, for odd, if I plug in a negative input and it's the same as the negative function, then it is odd. Y'all, look at this. here's a negative function, here's with a negative input of x. Guess what? Those two things are the same. Woohoo! So I'm going to write down here, negative h of x equals h of negative x, which means this function is odd. Yeah. Okay, let's go to 51. All right, y'all, so here is number 51. I did my best approximation of the graph. So they're asking you to find both absolute minima and maxima and local minima and maximum. So let's check this out. Remember that, let's start with local. Remember for local minima and maxima, those cannot be endpoints. So my endpoints are out of the game for local minima and maxima, which means I need to look and see where the function curves, where it's turning and creating a bottom and a top. So if I follow the function down right there, it turns and curves up, and right here. So these are the two spots that I'm looking at. Coincidentally, these are also the absolute. If I'm looking at the whole function, it's the absolute top and the absolute bottom. Here's the problem. Those are both open circles, which means my function is not actually equal to 3, 2, not actually equal to -1, -3. So that means that for all of these, both absolute and local, there is none, because the point there does not exist. I know we're getting really, really close, so it seems to make sense that we should say, oh, that point exists, but it does not, because we are never actually going to get there. We will get infinitely close, which is why we can't say that we stop at like 2.9, because we will actually stop at 2.999999999, repeating forever and ever and ever, and I can't estimate that in an interval. So my final answer will just be none. Shablam. On to 61. Okay, so this question, y'all, is asking you to use a graphing utility and find the average rate of change of this function f of x equals -2x squared plus 4. So let me start by saying you won't be expected to do this on a test, but this just kind of shows you something that we can do using a graphing calculator. So the average rate of change, this is just basically the slope, right? So we're looking for the change in y divided by the change in x. So if we can figure out how much the y value has changed and then divide that by how much the x value has changed, that's what we're trying to find. So what they have given us here, these are the x values. So when x equals 0 to x equals 2. So if we look at our calculator, and I'm going to show you, I think I can do this, I'm going to show you my calculator. Huzzah, calculator. So this is what my graph looks like, and what I did here is I hit the trace button, this guy right here, trace, and when you hit trace, you can type in a number. So I typed in the number 2, enter, and then it said, okay, this is what, when x is 2, this is what your y is equal to. So I know that right here, that point is 0, 4, and I know that this point is 2, -4. So then for my change in y over change in x, I can just say, oh, okay, so 4 minus -4 divided by 0 minus 2, and that gets me 8 divided by -2, which is in fact -4. So my average rate of change for that interval is -4. And then I can just do the exact same thing for the rest of those guys. And you should get a rate of change of -8 here and a rate of change of -10 for that last one using the trace function. Again, this won't be on your test, but yeah, there it is. Okay, on to 75. All right, y'all, this one has us doing some graphing with the graphing utility. We have a word problem where the average cost per hour in dollars of producing X riding lawnmowers can be modeled by this fancy-dancy equation right there. So the first thing we need to do is use a graphing utility to graph that function. So I did that. Let me get a picture of that in here. Okay, voila, that is the function that I have. I had to zoom way out. I think my window is, my x minimum is -100 all the way up to an x maximum of 100. And then my y-axis is negative 1,000 up to positive 1,000. So it's a big graph. Okay, so what they want us to do is determine the number of riding lawnmowers to produce in order to minimize the average cost. All right, y'all, so here is the deal. We know that this function represents the average cost, so we are looking for the minimum of this. Now, if you look at all this back here, it looks like there's an asymptote, which makes sense because we can't be equal to 0 right there, right? So the x equals 0 is undefined, so there's nothing there. But here's the thing, this, if we were on this side of the function, we would be making negative lawnmowers. Since we live in the real world, we're making positive lawnmowers, so I'm only going to be looking at this side of my equation, right? So what I'm going to do is I'm going to get in there and I'm going to use the second trace button to get to calc, and I'm going to find the minimum of this point right here. Let me just put a point right there. This guy right there. That's what I'm looking for. So let me go do that real quick. Okay, y'all, so when I did that, I found the minimum, which is in fact right there where that little x guy is. The minimum is x equals 9.6591586 at, the y value, I should say, is the minimum 238.6, so that's going to be dollars, and that happens at 9.659 lawnmowers. So determine the number of riding lawnmowers to produce in order to minimize average cost. So what does our input need to be in order to reduce the average cost? It needs to be 9.659 lawnmowers. Now here's the deal, I can't produce 9.659 lawnmowers, right? So in thinking in a real world type of scenario, I am going to say that we are going to produce 10 lawnmowers per hour. So 10 mowers per hour. Yay! And then the next says, what is the minimum average cost? So then that's asking for our output, which is the y value, 238.653. So I am going to say at the minimum, let's just round it up to $239. Voila, there we go, done. Okay, let's do 76 real quick, which I'm pretty sure is very similar to this one, and then we'll be done with 1.3. All right, y'all, so here is number 76. We have another super long giant function with a word problem, this time dealing with medication in the bloodstream. So the first thing we need to do, since this is a graphing utility problem, we are going to use our handy dandy graphing calculator to graph this. So let me do that and get a picture up here for you. Okay, so here is our graph. Y'all, my window is pretty interesting, so I knew that I couldn't have negative hours, so I limited my x value to -1 to +12, I believe. And then for the y value, since it was asking for such small concentrations like 0.5, I made my tippy top y value, I believe 1.5, and then I'm counting by tenths. So that's what my window looks like, so that's why my graph looks like that. So what they're first asking us is after how many hours will the concentration be highest? So that means I am looking for a maximum, which means it's going to be somewhere around here, and I need to use my calculator function to figure out where that is. So let me do that real quick. And voila, using that function, I have found that the maximum is in fact 0.759, and that occurs when x is 2.16, so basically after 2 hours, or I should say just over 2 hours. So after how many hours will the concentration be highest? After 2.1, oopsie, I wrote the wrong thing. That's erase 2, oh golly, okay, 2.16. 0.16 hours. Okay, the next question is asking, a woman nursing a child must wait until the concentration is below 0.5. Look at this math in real life right now. Before she can nurse again. After taking the medication, how long must she wait? So to do this, we are still using our calculator, and there are many different ways to do this. I'm going to give you kind of a, not a cheater way, but just kind of a shortcutty way. There are ways to use your calculator to get in really, really nitty-gritty to these functions, but I don't want to do that right now because I don't want you to get bogged down with that right before the test. So what you can do is you can hit the trace button right here. Dun, dun, dun. Hit that guy, and then just use your arrows to scooch down until you see Y drop below 0.5. Very, very technical. Let's do that. I'm going to take a picture of what my calculator looks like when I do that. Okay, so here's what I got. I was at 0.51, and then I dropped right here to, whoopsie, oh my gosh, I did not mean to do that. I dropped down here to 4.89, oh my gosh, 0.489. So y'all, that is below 0.5. So what I would say is it looks like this nursing mother has to wait approximately 4.5 hours. Again, this is just an approximation. There are ways to figure this out much, much more accurately, but this is what we're going to do for now. Please know that I will not ask you to do this on a test, but again, these are just helpful skills to have when using your graphing calculator. All right, y'all, that is 1.3. I'm going to move on to 1.4. So that's next. Let me know if you have any questions about this. All right.